participants are in listen-only mode. Go ahead, Ralph.
Okay. Welcome, everyone, and welcome to today's Getting to Zero webinar, Strategies for Getting to Zero. I'm Ralph Dinola, CEO of New Buildings Institute, and I have with me today Charles Ely, Principal of Ely and Associates, Patricia Andrasik, she's Assistant Professor and Head of Sustainability at Catholic University of America, Michael Tillou, he's Associate with Atelier 10 Environmental Design Consultants and Lighting Designers, and Mark Parapolitza, Director of Sustainability and Technical Design at SERA. Before we begin, I have a couple of housekeeping items to tell you about. First, you are all muted. We do this to keep background noise down, and so everyone can hear better. I wanted to direct you to the dashboard on the right side of your screen. If you're having technical difficulties, you can go to the question pane and you can chat with our staff and we can resolve any challenges you might have. We'll take questions and have discussion at the end of the webinar, but you can ask a question anytime in the question pane on the dashboard. You'll be at the end of the webinar, you'll be given a short survey. We ask that you take the time to complete that survey, and with as much detail as you can. It really helps us to provide additional webinars and more content that you might find interesting or necessary for the work that you're doing. You will also have the opportunity to enter your AIA number for credit for this webinar at the end of the survey. So I will introduce each speaker as we go through the webinar today. So let's begin. First of all, I want to thank our sponsors. The sponsors of NBI make all of this possible, and we're grateful for their support and contribution to our efforts as we work to realize our mission at NBI. And at NBI, we're really working to advance energy efficiency in the commercial building sector, and we're really working to provide solutions that help to make this change possible in the built environment. We have more upcoming webinars that we would appreciate you joining as well. So in April, we're going to be talking about Beyond a Building, so we're talking about getting zero to scale. And then in May, we will have ZNE policies and across borders, and this is looking at what's happening with getting to zero nationally and internationally. So I want to just begin with some context. Back in December, over 190 nations met in Paris to come up with an accord to keep temperature rise below 2 degrees increase in Celsius. And with that, I think has really, they've really begun a movement internationally to work on driving down greenhouse gas emissions. And so I think with this, we have a kind of a new initiative happening nationally and internationally, and we have a good rationale for the work that we're doing. And I think at the same time, it's worth pointing out Arup and C40 Cities released this study called Potential for Climate Action, and in that study, they pointed out that in terms of first priority actions for reducing carbon emissions, that buildings play heavily. In fact, buildings provide the best strategy for first priority actions for greenhouse gas emission reductions. And so we would like to, focus our efforts around zero net energy buildings and really tackling this first priority action through the building sector. For the past several years, NBI has been tracking zero net energy buildings nationally, and we have, with our current database, we've tracked the ZNE building activities that are happening across the nation, 40 different states in the U.S. You can see also provinces in Canada, and every climate zone in the U.S. represented. And our data is showing a great growth in the number of buildings that are either verified or emerging as zero net energy buildings. And Please keep in mind that these are the ones that we're aware of, but if you're aware of projects that may not be in our database, we ask that you enter them into our registry and database. Recently, we released a study that we did for the Continental Automated Buildings Association on zero net energy buildings and the controls in those buildings. This was a survey of 23 buildings that are either ultra low energy or zero net energy. To understand the way controls are working and if they're effective and what some of the challenges and opportunities are. I think one of the key findings in there that I wanted to share is this idea of setting the target for zero net energy, which is actually a big part of what our panel will be discussing today, is targeting zero net energy and what strategies can you use to get there. And I think the statistics here are really pretty important to see. That of all of the survey respondents, 29% thought setting the target for zero net energy early was very important or critical to success. So 71% saying it's critical to success. So you can see here, none of the respondents said it's not important or somewhat important or even important. It is critical or very important. In terms of our results from our survey, we find that modeled energy use intensity and metered or actual energy use intensity can vary, and also the ultimate outcome of net energy use intensity in these facilities can vary. But again, the target for Z&E was one of the critical factors in achieving success. We also found that controls are a key driver of achieving Z&E, and the question was basically asked, are controls important? Absolutely. And would you select the same controls again? The majority say yes, but there are lots of qualifications in that response. And we also know from our research that designing to the Z&E target and designing for performance and a focus on operations and occupancy is really important. So we're driving a lot of activity around that. And the other thing we recognize is that it's really important to integrate the people that will be operating the facility into the design process and the design team into the operating process. So we want to bring that facilities team into the design process and make sure that there's continuity with the design team through operations to close the gap that typically exists in conventional building development. And commissioning is key, and perhaps even redefining commissioning for zero net energy performance is something that could be considered as we move forward with Z&E buildings. And then, of course, basically operating to that zero net energy target and measuring and verifying performance is key, and engaging the occupants and the facilities team as well. So just in summary, we are advocating for setting that zero net energy target early, designing to that target, building to that design, and operating to the target, and then measure and verify performance as you go, and knowing that zero net energy is not a destination but really an ongoing journey. So with that, I would like to move to our next speaker on the panel, Charles Ely. Charles is an architect and mechanical engineer with more than 35 years experience in energy efficient and sustainable design. He's made a significant contribution to the California energy standards, ASHRAE 90.1, and energy codes in Hong Kong, Hawaii, Guam, American Samoa, and Australia. In addition to his energy code and policy work, Mr. Ely has developed a number of important publications, including the Advanced Lighting Guidelines, Lighting Fundamentals Handbook, as well as numerous other technical manuals on energy efficient and code compliance. So with that, Charles, please take it away.
Okay, thank you very much, Ralph, for that nice introduction. Next slide. What I'm going to do today is just present sort of a high-level feasibility analysis for Z&E in the United States. Next. Next, and hit it again, Ralph. So this is a map of solar insolation in the United States. Next. And what this shows is kilowatt hours per square meter per day on a surface that's tilted to the south at an angle equal to the latitude. So the Southwest has the greatest solar, the Pacific Northwest has maybe the least. Most of the country has 5 kilowatt hours per square meter a day or more. Next slide, Rob. So what I've done in this presentation is I've divided the DOE and ASHRAE thermal climate zones into 8 regions, which are identified here, and I'm gonna give kind of a very brief analysis of the feasibility of Z&E in each of these climate regions. Next slide. Next. Yeah, okay. Yeah, there they come. There's a lot of factors that affect PV production, and here's just a few of them. The orientation and tilt of the collectors. Shading is a huge factor. When you tilt the collectors, there's self-shading issues that require that you space them so that they don't shade each other. And also, you know, there's the collector efficiency and the inverter efficiency and all of those issues, which are continuing to improve. And we've seen dramatic price declines in solar energy in the last 10 years, especially 5 years. Average costs are now in the range of $2 to $3 a watt. Next slide. So what I did here is for each of these climate regions that I identified, I calculated the kilowatt hours per kilowatt at the optimum tilt. I also that's the first column. The second column, I calculated the kilowatt hours per year per kilowatt of capacity in a horizontal orientation. And then in the last 2 columns, I converted it to square feet of collector area. And this is based on about 65 square feet per kilowatt of collector area, which is an average for modern monocrystalline panels. Next slide, or next click. So the thing is, if you want to create maximum production on your site, and it's actually better to orient the panels in a horizontal position, or to slope them slightly towards the south, but in one plane, so they don't shade each other. An example of a building that did this recently is the Bullitt Center in Seattle. And for a given area, you can actually receive maximum production that way. You may have to buy a few more panels because the production decline is a little lower, as you can see in the first 2 columns for horizontal versus the optimum tilt. Next slide, Ralph. So the next part of the feasibility is to look at the site energy utilization index, which is shown here on the vertical axis. The climate regions I developed are shown on the right side, starting with the mildest climate, the Pacific coast, and moving to the most difficult climate, the Arctic, in the back. And then I did the same thing with the building types along the front. The first row are warehouses, then offices, retail, schools, apartments. The orange line are offices that have a data center in them. Then there's hotels, healthcare, and finally restaurants. And so that you could see this in more detail, I didn't The restaurants actually blow off the top of the scale up to close to 400 EUI. So these are typical EUIs for buildings that comply with ASHRAE Standard 90.1 2013, which is the latest published version of 90.1. Next slide, Ralph. So what I'm showing here is the maximum technical potential. And this is from a study that Jason Glazer recently finished for ASHRAE. And it's based on modeling. And he looked at all of the technologies that are feasible and reasonable for buildings and applied them, including some plug load issues and things like that. And you'll notice that these EUIs are significantly lower than in fact, they're about, on average, about 50% lower than minimum compliance with 90.1 2013. Next slide. So what I'm going to introduce here is the concept of collector area to floor area ratio, and show what that number is for these various situations. So if that ratio is 0.33, then you would need to cover 1/3 of the roof of a one-story building, 2/3 the roof of a two-story building, and you need to completely cover the roof of a three-story building. Next slide. If the ratio is 0.5, then you're beginning to look at problems with three-story buildings. You could get there by covering the roof two-story building. Next slide. And then if the ratio of collector area to floor area is 1 or more, then you're going to have some real problems in achieving Z and E for all but one-story buildings. Next slide. So what these tables show, the top part of this table are buildings in compliance with 2013, and the bottom part of the table is for buildings that are designed to the maximum technical potential. And the areas shaded in black are areas where the collector area to floor area ratio would be greater than 1. The areas in the light gray are 0.5, between 0.5 and 1, and so forth. So you can see that if you look at the bottom line, most buildings are going to have the potential to reach Z and E without a lot of problem, unless they're high-rise towers or something of that sort. Next slide, Ralph. So another way to look at this is the maximum floor area ratio. The floor area ratio is a planning concept where you divide the building area by the site area. So in this case, the floor area ratio is 1. Next slide. And if you have a 0 lot line configuration, it's the floor area ratio is basically the number of floors that you have. Next slide. So presenting the data in a slightly different format, you can see the maximum floor area ratio that you could have in order to achieve on-site Z and E. Looking again at the bottom part of this graph, restaurants are the main problem. Healthcare is also an issue in the cold and humid climate, and several building types are a problem in the Arctic. Fortunately, there's not a lot of construction in the Arctic. And the interesting thing is that if you look at the construction area or the volume of construction activity for different climate zones and building types, the vast majority of those building types and climates are in areas where Z and E can be achieved relatively easily. Next slide, Ralph. Next slide. So just to summarize, this is sort of the equation of for Z&E. You multiply your floor area times the EUI, and you subtract the collector area minus the production area times the PV production area. So the first strategy would be to reduce the floor area if you can. The second option would be to design to as low an EUI as is technically possible. There's theoretical limits to that unless we, have a major paradigm shift like eliminating burgers and fries from fast food restaurants. But the next option is to increase the collector area, but this is limited by the area of the site. And the final option is to just increase PV and inverter efficiencies, but there's also theoretical limits there. Next slide, Ralph. So there are some off-site strategies. One strategy is to combine the challenged property with other properties through virtual meters or some other technique. Next slide. Another option is to install renewable energy on a remote site. Stanford University is a good example of this. They're putting in a 73 megawatt solar farm in the desert that's going to offset about half of the electricity use on the campus. Next slide. In many areas, community solar systems are beginning to emerge, and one option would be to buy a share or to lease collectors in this community solar system. Next. And then the final option would be to purchase renewable energy certificates or RECs. And in my opinion, this is the order that you should pursue for off-site options. So this is the next slide. So that's the end of my presentation. This is kind of a top-level feasibility assessment for Z&E buildings. I think the bottom line is that it's totally feasible for all, except for restaurants, which are going to be a problem, and in some areas, healthcare and hotels are going to be a challenge, but it should be possible. And the second thing is that when it's not possible to do it on site, there are some reasonable options for achieving off-site Z&E as well. So thank you for the time, Ralph, and I'll take any questions or let you take over.
Thank you so much, Charles. That was really fantastic. A great summary of strategies, and I appreciate that last slide, which gives us kind of an order to priority for what we're doing. So we'll hold questions till the end, and thank you again, Charles. We'll now move to Michael Touloux. As Atelier 10's energy analysis practice leader, Michael Touloux brings 17 years experience as a mechanical engineer and energy analyst. His expertise includes HVAC control systems analysis, design engineering, energy modeling, commissioning, optimization and troubleshooting, sustainability consulting, energy auditing, benchmarking, demand-side energy planning, and technical engineering support services for energy performance contracts. He's worked on a wide variety of institutional, university, healthcare, and laboratory projects, including those for Williams College, several SUNY campuses, George Mason University, Novartis, Mass MOCA, Veterans Administration, Nova Southern University, and Oak Ridge National Laboratory. Welcome, Michael.
Thank you, Ralph. Next. So my talk today is really from the perspective of a practitioner, and at Atelier 10, our approach to net zero energy is really very process driven. We found that it has to be in order to achieve the goal of a building that produces at least as much energy as it uses. Next. And so part of our practice is very clearly defining the framework around which we hang those processes. We have very strong principles, guiding principles, and that's to design from first principles using integrated design process, trying to be very pragmatic about strategies, and then using those principles to really develop the overall strategy for a project. Next. And so I'm going to talk a little bit about how we've successfully applied this process for net zero energy buildings through a series of 3 case studies that are really going to sort of hit 3 different topics. One, the importance of starting early, as Ralph started us off by sharing. Having a vision for the long term. And this is really something that we don't see very much of from our clients, and it's something that we've been educating them about, and it's really the idea that a building doesn't have to be net zero energy on day one. You can plan for it to be net zero energy over the life of the building or at some future date, but it's important to plan for that now and then implement it over the long term. And then finally, the importance of not forgetting the small stuff when you're designing a net zero energy building. Another important thing that we have to educate our clients on is that every single thing that uses electricity or energy in your building has to be accounted for. Next. So the first case study I have is a project I worked on about 8 years ago. It's a college admissions building in Texas that was being designed by Canon Design. Next. And this project really illustrated that you can never start too early. And I was asked to participate in this project, and basically this is what I was given. I was given a watercolor drawing of the vision of what the architect wanted to design for the building, and that's about it. Next. And from that, what we did is we took and we built a fairly robust prototype model based on the program areas that they discussed with the client, and we created an energy budget. And from that energy budget, we were able to refine it to the point where we were able to show that, with a set of assumptions, we could achieve net zero energy for the project. Next. And what that allowed us to do is really in pre-schematic design, we were able to set some very aggressive performance targets that the project team would have to achieve in order to get this building on a path to be able to meet net zero at the end of design. And I think the highlights would be that instead of talking about plug load energy and lighting energy, which we typically describe as a density, a watts per square foot number, in this case, it's important to talk about these types of energy uses as consumption targets. So how many kilowatt hours a year per square foot are you allowed to consume? And this changes the conversation a little bit, because now, taking lighting for example, it's about not only designing the light fixtures themselves to use less energy, but it's also about the controls that are controlling that lighting and how it delivers an integrated system that's going to minimize energy use throughout the entire year. Next. Okay. My second case study is a little more recent. This is a GSA federal building that was designed by Crook and Sexton. And the interesting story about this project was, as I mentioned, having this vision for the long term. Next. And so one of the first things we did on this project was looking at all the different renewable energy strategies that could be incorporated and could contribute to achieving a net zero energy. And you can see here the difference, the shading is representative of the actual footprint area of the different technologies on the site. Because in addition to understanding how much energy a system could produce, we also wanted to be able to quickly convey the magnitude of how much area on the site it would take up. So you can see that PV obviously has a much larger footprint than, say, thermal energy storage or a solar hot water system that's designed to offset the domestic hot water use of the site. And we can use this in the planning process once we set a target. Next. And so once we had strategies and did some modeling, we basically looked at some different scenarios. Next. And the project chose to target an ENERGY STAR 95 score. So it didn't target the most aggressive building energy performance that it could. And really this was striking a balance between first cost and performance and the magnitude of the renewable energy systems that would be required to hit net zero energy. And so that's why it's important to sort of bookend, and then you can do this optimization analysis to find the right target. Next. And then with that target, the team was able to go and design a building that met that performance. Next. But really the most interesting aspect of this project wasn't that it was designed to be net zero energy. It was that it's designed to be net zero energy at some time in the future. The project couldn't afford to be net zero energy on day one. And so on day one, the building was designed to only have about 17% of the PV it needed. It had all of the it had about 30% of the solar hot water that it needed to get to net zero energy. But there was a plan that was created to allow the building to expand the renewable energy on the site to achieve the net zero energy goal over a 10-year period. And as you can see, that it was a phased approach that adds PV to additional roof and parking, and then sort of continually adds PV until at the end of 10 years they would be achieving net zero energy. So I think this is, too often we come up against clients that just sort of think about it as an all or none. You know, oh, I have to do net zero energy all in or not at all. And my message would be, it doesn't have to be. Phase it in over a period of time and at least design the building and the site so that you can achieve net zero energy in the future. Next. And then finally, my third case study is a project, Frick Park Environmental Center in Pittsburgh, that was designed by Boland Sawinski Jackson. And this is really about not forgetting the small stuff. Next. And so this Frick Park is pursuing Living Building Challenge. And for those of you that don't know, Living Building Challenge certification is sort of like LEED on steroids. And one of the things that you're required to do is to be a net zero energy building. And so the project started with early design concepts. Next. Then it sort of, moved into the more detailed design phase. And really what happened at this point is the client started to introduce all the other things that they needed for the site. Like they have gatehouses that sort of are the entrance to this park site. They had a barn and service yard. They wanted to incorporate a fountain as part of the landscaping design. And all these things needed to be incorporated into the accounting of net zero energy as part of the Living Building Challenge certification. Next. And so as the design progressed, we went and there was a big fountain feature that was added to the project that was not really in there originally in the original design concepts. And of course, as you can imagine, a fountain has pumps and filters that use energy. Next. And so you can see that the accounting of this really changed sort of late in the design the approach to net zero energy. And we needed to account for this to make sure that there was enough photovoltaic energy or enough photovoltaic panels. The renewable energy design had to be increased to account for this additional plug load energy. And as you can see for this particular site, the exterior energy use was about 25% of the total annual energy use. And if it had been forgotten, would have really made a big impact on, well, the project wouldn't have been able to achieve the Living Building Challenge. And so it's really critical that you carefully account for all of the different pieces of equipment that are on the site, even things you don't typically associate with the building that might be outbuildings or landscape features that are going to use energy as well. Next. And so I would say, again, from that process standpoint, it's never too early to start. It's critical that you design energy metrics for both the design and the operation of the building. Don't be constrained by designing for day one. If your budget can't afford it, plan for the future. Plan to achieve net zero energy at some point 5, 10, 15 years after the building opens. You have to continuously track your project throughout design to make sure that you're on task and that changes haven't popped up that impact your budget. Don't forget the small stuff, and you have to establish a process and stick with it. Those are really the sort of drivers for successful net zero energy building. Next. And that's all I have, and I will hand it back to Ralph.
Great, thank you so much, Michael. That was excellent, and you know, I appreciate the way you've summarized those critical steps, and I think that's going to be very useful for the folks that are participating in this webinar today. So next, we're going to have Patricia Andrasik, and Patricia, let's see, I'm going to move one ahead here. There we go. Patricia's practice and research stems in building performance analytics, human factors, and third-party green certification as a means of improving sustainable building design potential. This course of work has since evolved to study facility performance evaluation and has been recognized internationally in publications and several conferences, and recently earned a Presidential Teaching Award at CUA for developing 3 new courses which offer quantitative and qualitative performance analysis. She holds a Master's of Architecture degree from University of Oklahoma and has completed graduate work as a Fulbright student scholar and at the Technical University of Slovakia, and taught as a visiting professor of architecture in Beirut prior to returning to the U.S. to practice. Please welcome Patricia.
Thank you, Ralph. Thanks for that introduction. Next, please.
Okay, and I've just handed you the controls. Try and see if that works.
Great. Thanks. So one of the most important strategies for getting to net zero is establishing a methodology of application. And how will you perform an iterative analysis to maximize passive strategies? And that's by integrating tools. According to the NREL, net zero building is one that greatly reduces the energy needs. And it comes in 2 steps. There's a passive optimization first of the building before the mechanical optimization occurs. I've been in practice for many years, but it was really through teaching that I had to recognize the steps in net zero design, starting from passive design optimization using these tools. The ultimate goal is energy reduction using passive strategies first prior to renewables or any type of mechanical intervention. And teaching our young architects to embody this idea starts from the BIM sustainability wheel, which explains how building performance analytics is integral to driving the design process all the way to the operations and maintenance phase, similar to what Mike had alluded to. We're teaching students not to stop at the occupancy, but to continue, and we're teaching them tools that can go from the onset of design into facility information modeling using BIM tools. So with respect to building performance analytics, we can define VPA basically as a series of tools used by architects in the process of evaluating performance prior to energy modeling. The tools are associated with topics of environmental conditions which require understanding. And as you can see, there are many different topics. Various software can attain certain performance analyses, and environmental factors are applied to passive strategies, but namely those that impact energy. There are 4 main categories that I've identified with respect to optimizing passive strategies prior to mechanical intervention in sustainable design and net zero design. These are solar potential, which is daylighting, solar radiation, shading, electric lighting. Climate, CEA, conceptual energy analysis, airflows, whole building simulation, and thermal qualities. Through the past few years of teaching building performance analytics as a new course, I've recognized certain patterns that students are using these tools in to create their designs, the studio projects and projects within building performance analytics class. I've collected these methodologies and deemed them methodologies of BPA integration. Through studying many of these, both in the classroom and outside, prior to my entry into full-time academia when I was practicing, I recognized that certain factors need to be grouped together to maximize ease and fluency in maximizing potential optimization of some of these early sustainability objectives. Solar potential is one of the most important, and it spans 4 different categories: shading, solar incident radiation, daylighting, electric lighting. Project climate data is more of the static element that really can't be changed so much when you're doing performance analytics. Conceptual energy analysis, CEA, is one that studies EUI at the onset of a project very preliminarily and then starts to increase the specificity as the model is informed with context with materials. Thermal and airflows also are in tandem with the conceptual energy analysis studies. The various interpretations of how these tools should integrate into the design process have been explored and are continuing to be explored, but a few conclusions can be documented as static and dynamic iterations of integrating tools to define an iterative analysis. This is the climate tool. Climate Consultant is the nominal and the most outlasting tool that's been used to study climate, radiation, precipitation and wind flow, wind direction, and this is probably the most commonly used building performance analytic. This would be a static iteration. Since the climate and the climate files are the only elements that are going to change in the analysis. These static iterations are climate data. These which can be retrieved from TMY files, but not typically modified so much during the analysis unless, of course, your site changes. The dynamic iterations really occur as certain analyses are clustered into these logical pairings. For example, conceptual energy analysis. So the next few slides, probably 7 or 8 slides, will demonstrate the application of the integration of these tools in that methodology of clustering analytics. Conceptual energy analysis, which many of you are familiar with, can be accomplished through a variety of tools nowadays. In this example, we're taking a standard building and we're trying to identify the maximum orientation, the most potential optimization for orientation, and then we're also exploring fenestration percentages with that. And at the same time, we're beginning to identify what sort of shading devices would be used. So how do we determine preliminary energy efficiency via how we shape our building? I like to call this form, fenestration, and orientation as the first step of conceptual energy analysis. In the second step of the dynamic studies, the airflows are optimized. This includes identifying natural ventilation potential, blocking unfavorable wind potential, particularly in the winter in different climates, and also studying contextual impacts of wind. Where can we locate the living room, for example, in this unit to the left, to maximize double-sided ventilation? And on the example on the right, in the residential tower design, which site promises the best shading options without decreasing wind velocity? The next dynamic study is the hygrothermal study. And in the example that I'm showing you, we're using the tools of WUFI and Therm to identify dew point, and we're also identifying the rate at which infiltration may or may not occur. These two combined together will show us the ratio of water vapor to air may be at risk of reaching 100% RH condensation at a certain point, which is right here. This is a SIP panel that we're analyzing in a California climate. So in this Therm example, by keeping the dew point line farther from the interior wood stud, which this is the interior, moisture and mold are potentially reduced. After studying the hygrothermal, we take a look at the solar potential synergy, is what I like to call it, where we study simultaneously shading, solar incident radiation, daylighting, and electricity, because they're so symbiotic. I've got a few slides on this. The left-hand slide shows an airplane hangar about 1,300 feet long, pretty long, but very narrow. Contractor was asking how many skylights would be needed to meet LEED for this building, for this facility. At first, I wasn't sure, ran a quick study in 3D Max, and recognized that there was absolutely no skylights that were needed that we achieved within the LEED requirements. This was a LEED project between 25 and 500 foot candles without any skylights whatsoever, and that was a quick 3ds Max study. In the right side, we had a client that was studying whether or not it would be cost efficient to employ a sophisticated sun shading screen. We took this study into Ecotech, which is now obsolete. It's no longer downloadable. But at the time, a year and a half ago, we recognized that the more complex shading structure that you could see in the middle actually yielded very similar shading to the shading structure that only had minimal shading. So that was a cost-saving potential for the client. This is our solar decathlon submission, and we tied in a couple of strategies here, and this probably describes very nicely the synergy of daylighting, electricity, solar shading, and incident radiation that I was describing. We originally designed a shade screen that was 3 inches wide, 3-inch spacing. I took a look at a couple of different options to see if that was in fact the best option for this California climate. We discovered that actually an 8-inch deep screen and the 3-inch screen, deep louvers, were pretty similar. But what was interesting is when we took it to a daylight study, we recognized that we were able, due to the bounce of the sun on the depth of the louver, we were actually able to slightly decrease the electric lighting inside of the small kitchen space, because the amount of light that bounced from the longer louver provided a little bit more daylighting. It was just a couple of foot candles, but in a small space, a couple of foot candles really means a lot. So with this study, we were able to synergize all 4 different aspects of the solar potential to come up with a conclusion that we didn't end up building, but we end up discussing at the very end as something we should have looked at much earlier in the design process. This is an insulation study where this was a student project, and the student was asked to analyze the same shape, size building for the maximum orientation and shading mechanism of a certain climate using different types of studies, different types of shading devices that were modeled and then tested. Taking that final conclusion, the best solution, which was option C, which yielded the lowest, the highest energy efficiency, the best EUI, to another study, to a second study, which was the energy modeling phase. Artificial lighting with daylighting is also very important and a part of that lighting synergy that I discussed earlier. This takes a little bit more time, especially if you're designing the lighting independently of the daylighting study. That means the 2 different analyses need to be run simultaneously. And this is an example in solar analysis in Autodesk, where we have a rendered model of the interior. This is the floor plan, and this is the RAS, which is the lead daylighting software plugin for Autodesk, describing where the greatest amount of daylighting is coming in, and as opposed to the artificial lighting. So the integrating building performance analytics tools into the design process has definitely challenges and benefits. The challenges are training. A lot of people need a little bit of time to train on some of these tools to understand what the analytics are really describing in their project. Some of that time may not be afforded in practice. Some of it's not even afforded in one semester in school, even in studio class. Some of the challenges include also product selection. Various manufacturers are constantly evolving their tools. From the presentation that I presented last year, I had to change many of my slides because the tools simply were obsolete. Ecotech being a favorite, especially of mine in incident radiation, is now not downloadable anymore. So other manufacturers are adopting that software into their mainstream and constantly evolving that software. Interoperability also is a challenge. Interoperability into the design process of your firm or institution or with other building performance analytics software. What's the basis? Some of it has more of a Revit basis, some of it is more based on a Rhino model, building information model. Some of the benefits include education. Most software and the tools that are available come with a free education. The benefits of the Academy produces skills symbiotic with the firm's needs. We're training students to aspire to what the firms need. And here in DC, we have a good idea of what the firms are needing because we're so close to them. So we're trying to train our students so we can aspire to what they're needing in their firm, even if students are bringing this knowledge of BPA methodology into the firm themselves. And also compatibility with energy modeling software. The tools after the BPA software are the energy model. So we have to make sure, and most of them are compatible with the official energy modeling software. So in summary, this is the synergy that I have created based on a couple of years of research of the best synergies of building performance analytics. You can find more information about this in JNIB's article last summer, where this methodology was published. First step being climate data, which is static, and then the two dynamic aspects of building performance analytics are conceptual energy analysis, wind, hydro, and then the solar potential quartet. All of that yields to the energy model, and you can see I have in red the various software that is available for studying these various aspects. And then my final slide creates one diagram to express the collective integration of these synergies and how they work in creating a methodology of integrating tools for building performance analytics. I want to also mention at CUA we are now exploring really how to democratize high performance design by embarking on projects where we implement this methodology to design housing for some of the marginalized populations, specifically a recent grant to design transitional refugee housing. So we're not just saving this for the high-profile clients, we're also using this for some of the clients that may be a little bit more marginalized, but still are ever in need of the net zero design and high-performance strategies. Thank you.
Great. Thank you so much, Patricia. That's a really fascinating methodology and what you've assembled in terms of the analysis approach. So look forward to some discussion and Q&A on that. And next, I think, we'll move to Mark. So as Director of Sustainability and Technical Design at SARA, Mark Parapolitsa facilitates application of the team's expertise and services within SARA's project teams. His expertise in climate-responsive building enclosures has helped project teams and clients pursue aggressive energy goals while enhancing occupant comfort. Mark has over 20 years of experience in architecture and has played a significant role creating quality public buildings in Oregon, Washington, California, Colorado, Minnesota, and Ohio. Please take it away, Mark.
All right, thank you, Ralph. Could you go to the next slide, please? So I'm going to talk about some lessons that we've learned from a recent project that was completed. This is a federal office building in downtown Portland, Oregon, that's been operated now for a couple of years. And we have some actually pretty interesting post-occupancy results back from that I want to share with you. So we go to the next slide. The building is actually is a deep retrofit of a 1970s era building. It's an 18-story building, and there were very ambitious goals for performance around this building, and it did indeed achieve LEED Platinum, and is performing actually quite well. And we'll talk a little bit more about some of those details today. So next slide, please. One of the things that I'm just going to focus on specifically is the importance for net zero buildings and any building that's, has very aggressive energy goals of really integrating the approach to the building enclosure, in this case the facades, with the HVAC. So that was a very rigorous process in the design phase of this building with multiple team members. The next slide, please. So the team looked at a whole series of strategies, combinations of measures that yielded various results, and you can see from the left there with a good envelope and a VAV system, and then improving it. But ultimately, it was realized that to achieve the levels of performance we were looking for, that we needed both the best envelope that was reasonable for the building, as well as, basically the best system, which is to say a radiant system where we would decouple the ventilation needs of the building from the heating and cooling side. Next slide, please. There are multiple advantages to radiant system, and that were definitely realized in this project. They're listed there on the left. I won't read through all of them, but a lot of it had to do with the performance, but there are also some real spatial benefits to doing it. And in this case, because we're it's a retrofit of an existing building, so we were constrained by that existing structure. The floor height and the floor plate were fixed. So any benefits that could be achieved in terms of less ductwork volume in the space was really significant. Next slide, please. But one of the things that was really critical with going to a radiant system and separating off the ventilation air as a dedicated outdoor air system is that there's a limited capacity with this type of radiant panel system to remove heat from the space. And so it was understood from fairly early in this process, working with the team, that the heat load on the building needed to be reduced. And if it could be reduced to the level that was within the capacity of the radiant panels, then the project could succeed. If not, then it wouldn't work. So basically there was sort of a budget that was established for how much shading needed to be provided to the building. Next slide, please. So the process of design and analysis involved both digital models and physical models to really understand multiple aspects of the, both balancing the solar heat gain with the daylighting intentions too, trying to get as much daylight as possible, both for the multiple benefits for the occupants with their health and well-being, as well as reducing the energy by offsetting electric lighting through integration with the control system. The next slide, please. And in the end, it was realized, not surprisingly, that specific strategies needed to be employed for the various solar orientations of the building. The building is the grid in the city, that part of the town, is shifted by about 15 degrees, and so it's not exactly true north-south. But basically, there was a strategy that was applied to found to be effective on both the south and the east elevations, and then a separate strategy for the west elevation, and then the north elevation received a small enough amount of direct gain that no additional treatment was deemed necessary. The next slide, please. So on the west, basically there is a series of vertical reeds, and for anyone that's followed this project, there was a period when there was a desire to actually do a living wall and to see if the shading from that living wall could actually provide the solar management for that side, which is a really compelling strategy, but unfortunately it involves a lot of risks if you're actually depending on that. So instead of that, a series of aluminum reeds, we refer to them, were designed for that face of the building, with some plants growing up it, but not depending on them and their sort of over time to actually design the system. Next slide, please. And then there is a sloped roof plane above the building that does incorporate solar PV. Now, of course, with a building of this scale, we weren't trying to actually achieve net zero, but it was a way of both engaging with the solar potential of that site as well as rainwater collection. So there is a harvesting system where the water is collected from the rooftop, and a former firing range in the basement was repurposed as a cistern, so that was waterproofed and used to hold rainwater. Next slide, please. But what I wanted to focus on today primarily is the results from occupant satisfaction survey. Next slide. We actually ran a number of surveys. We had the opportunity to survey the occupants prior. So while this building was undergoing construction, the federal employees were moved out into primarily into two locations downtown Portland, one just a block away and the other about 5 or 6 blocks. And we worked with the Center for Built Environment at Berkeley with their standard survey and 2 custom modules to develop this online survey. And with the new building in mind, the survey was put together and then it was run while those employees were in their interim space. And the categories there are listed of basically a range of indoor environmental quality categories they answered questions on. The next slide, please. This just shows the location of the 2 buildings, the Edith Green Wendell White building there at the bottom of the screen, and then the other 2 shaded red squares show the locations of the other 2 buildings. The interesting thing in particular with the one closest to it is it was in some ways shared a lot of similarities in that it's a large, similar scale building, In this case, it's actually new construction, but also it received LEED Platinum. But it had a more conventional VAV system. So the results were interesting to compare with that system, VAV HVAC system, with the Edith Greens. Next slide, please. When we look at the overall results, they look generally good, and so we say great. We would always love to see even higher results, but we had generally, fairly high level of satisfaction. But what's really interesting about it is to drill down into the details. So it's one thing to, when you average out the results across the building, you see one result. But knowing that the difference of the solar orientation, then also with a vertical building like this, that there would be differences vertically. I filtered then into the results and divided the building into two halves and looked at results by each of the four orientations at the upper half and lower half of the building. And in particular, we wanted to see how well did those strategies for managing heat gain and comfort work on, particularly at the south and west. We know that they're going to be exposed to, during the summer months in particular, a lot of heat gain, and even in the other seasons into low-angle sun, and to make sure that to see what kind of results we were getting. The next slide, please. The thing that was interesting is that we found that those areas that we were most concerned about were the most successful. And in fact, we had a higher level of dissatisfaction, thermal dissatisfaction, on the north face of the building and on the lower portion of the east. And so this is actually valuable feedback to look then more closely at what's happening there and to work with the commissioning team and building operator to see how that can be adjusted. I think it's a matter of some enclosed office spaces and just the commissioning of the systems in those locations. The next slide, please. Overall, we find that the occupants actually are a little too warm. So especially when compared to the other building with the newer variable air volume system, VAV, which is kind of more of a conventional delivery and kind of a large volume of cooled air. That building actually had very high levels of discomfort during the summer months for people being too cold. So despite how much publicity that problem has, we still see, in even LEED Platinum buildings, energy being wasted to make people uncomfortable, which is obviously ironic and unfortunate. A great opportunity, though, to make improvements. We did not have that problem in this building. In fact, we had the opposite problem. We had people being a little uncomfortable from being too warm. And so it was interesting to look at their reasons for being too warm. Part of it had to do with less air volume moving. People were less used to that and a little bit less comfortable. And also, I think there are some ways in which this can be improved. The next slide, please. So just to sort of summarize a little bit the results. So the post-occupancy surveys are really a valuable tool for a number of reasons. First of all, they provide great feedback for commissioning and for further adjustment and fine-tuning the operations in the building. There are cases where sometimes actually energy is being wasted, making people uncomfortable, or even trying to figure out the right balance. In this case, the ventilation air is being warmed a little more and maybe is even a little overwarmed, given that the results we're seeing back. But there's a great opportunity to improve that. In terms of the overall energy use of the building, could we have the next slide, please? The goal during the design phase was to hit an EUI between 30 to 35, and we've tracked it. So this slide shows the usage of the original building, of a code baseline building, and then the modernized building, both modeled and the actual as measured over a 2-year period. So we're seeing about it was projected to be about a 45% savings, and indeed it is achieving very, very close to that. Next slide, please. And this actually is a graph that shows the actual use. So from the last year, you see the orange line. The building is operating at an EUI of 34, I believe it's 34.2, which is a great performance. We're very happy to see that. when we look into the results again of this, we realize that the natural gas use is actually quite a bit higher than expected, and other uses sort of are offsetting that. So again, I think there's an opportunity to go in and look at how that the dedicated outdoor air system, how that air is being heated and probably overheated a bit. The next slide, please. So just sort of looking at these strategies and what implications they have, what we can learn from them for approaching net zero buildings. Next slide. The primary strategy that I've been talking about today is the integrated facade and HVAC systems. Obviously, there's a lot more to it than that we've heard from the other presenters today and from Ralph. In this case, there are some big challenges, especially if you're really looking for net zero. With an existing building, of course, the floor-to-floor heights are fixed, and your floor plate is fixed, and it's in this case a rather deep floor plate, which limits the access to the outdoors. Natural ventilation is a very effective strategy, especially in the Pacific Northwest, and it would be great to see a building such as this be naturally ventilated. But there's also the balance with program, and in this case, there are GSA security requirements which make natural ventilation very, very difficult, in most cases really impossible. And then, of course, the PV potential, as we've seen in Charles and some of the other presentations, when you have a tall vertical building like this, 18 floors, there's just not enough roof area that you could actually offset the building itself. But it still can make a positive, overall contribution in reducing the energy use. Looking at the occupant results, the net zero strategies, because we're really trying to dial in the energy use, the comfort becomes a big issue. If we ignored occupant comfort, it would be much easier to achieve net zero, but obviously that doesn't make sense. We're making buildings for people. It is certainly very valuable to get the buy-in of occupants. The more the group of occupants is engaged with the approach, then the more they're willing to sort of use their own activities and dress to try and work in conjunction, with the building operations to meet those goals. In a large federal building like this with multiple tenants, that level of buy-in can be more challenging, or any kind of sort of large leased office building that could be kind of similar. It's much easier when you have a smaller group that's more bought into that goal, but I think over time that certainly is a great approach. So the post-occupancy feedback we found to be really informative, both on this own building and for its implications for further work, in particular as it applies to net zero strategies. And I believe that's it. Next slide.
Great. Okay, thank you, Mark. And thank you to everyone. I want to just take a minute before we move on to our Q&A and discussion and just mention that we would welcome everyone to join us at the Getting to Zero National Forum we have coming up in October in Denver, and that we are about to close our call for presenters. So if you haven't taken the opportunity, please do submit your abstract, and we certainly are hoping to have many of our presenters here in our webinar series be a part of that as well. And I will now move into the discussion. So just maybe a brief recap. So Charles gave us a really clear picture of the technical potential of zero net energy nationally, and his methodology of looking at the collector area to floor area ratio, which I think is really useful, and that floor area basis for getting to zero. So that's very helpful. Michael, a very kind of simple set of principles, never too early to start, have a vision for the long term, thinking about net zero ready if you can't get there the day you open, and really focusing in on the small stuff and tracking performance as you go. Patricia, fantastic description of this idea of clustering the analysis and the reality of the fact that many of these tools that we use are not necessarily interoperable, and some of them have a limited shelf life. They new technologies, new modeling analysis software comes and goes, and so there's a challenge there. But your methodology is very good and comprehensive and very helpful. And then Mark, Edith Green Wendell Wyatt is such a great case study, and that was a wonderful presentation. But the value of post-occupancy evaluation, when you've done this really integrated design and this project, which used the kind of an integrated project delivery method. What are the results you get, and so wonderful. So what I'd like to do is maybe first just ask the panelists, are there questions you have for each other, or does anyone want to bring together some thoughts based on what you've heard in this discussion so far? Okay, hearing none, I can move on to some of our questions we have from our folks on the webinar today. So here's one question, and I would certainly open this up to anyone. Basically, in addition to the discussion around design elements and Xeni practices, can any of you discuss the incremental or financial impacts that customers face, your clients, in their new construction portfolios for targeting high performance and Xeni buildings and building standards like this? So any one of you want to tackle that question about incremental cost? I think from my perspective, this is always the first question about Xeni buildings. What does it cost? So anyone want to take a crack at that?
Well, this is Charles. I'll take a start. The cost of solar has declined so much in the last 5 to 10 years, and there's also financing opportunities through leases and power purchase agreements, that the incremental cost for on-site renewable energy is almost nothing. Mm-hmm. I know of several projects where they've been able to install solar through power purchase agreements, and the price they pay for electricity is competitive with what they would pay for a normal utility connection.
Yeah.
On the other side of things, I think in states like California, New York, and others that have really tough energy codes, you're not paying a premium anymore for really good windows or for a lot of other high efficiency features. Those are now required by law. So I think the combination of declining solar costs and tougher energy standards is making the incremental cost close to negligible on building sites where you have space on the roof to achieve Z&E.
Yeah, excellent point.
The challenge is going to be to manage plug loads and to engage the occupants in the process. Mm-hmm. And I don't know how to place a cost on that or a price on that, but that's a key aspect that's going to become more and more important as we move forward.
Yeah, and I think I just want to recap. Yeah, definitely, the cost of renewables, we're seeing parity with grid utility energy in many states now, and we know that number is increasing. So yes, the ability to either do a power purchase agreement or basically finance the system to get those renewables to meet that challenge, definitely. And then you're right, the codes are driving technological advances in the building technologies. Was that Mark that was commenting?
Yeah, I was just going to say I agree with Charles. I think and particularly when we look at buildings that are more horizontal or smaller scale, that I think that you can come very close to that net zero range with pretty small increases in cost. I mean, certainly the energy use needs to be driven down the EUI to where that's achievable. The challenge definitely becomes in sort of the mid to large scale buildings. There's big improvements that are being made, and certainly the windows is a big part of that, but also just a very strategic use of glazing. There are a lot of high-end solutions that are possible too, but the question was trying to manage the costs.
Yeah.
So certainly I agree that it's becoming a lot more achievable on the sort of horizontal and medium and sort of smaller scale buildings. And the challenge though remains at the medium to large scale.
Right, and I think everyone is aware that the vast majority of buildings by number are small, under 50,000 square feet. So the potential of actually achieving it on both new construction in that size range and also existing buildings is pretty key. So Mark, while you're at it, I think there's a question here about what modeling software was used on the Edith Green Wendell Wyatt.
So multiple tools were used, and this project, it actually had a very long life, and in the early days, actually, the design phase was before I joined Sarah Architects, but in the early phases of it, Sarah was the team used multiple tools, including Ecotect. There was some concerns about accuracy of the results, and so they were sort of validated and then sort of started leaning a little more on the physical modeling tools. On the energy side, the energy modelers, they used eQuest, but there was a need to really understand the thermal conditions, and so the Center for Built Environment has an advanced thermal comfort model, so basically a simulated mannequin in space with a sort of multi-layered body parts. That was used in conjunction with IES by the engineers to have a very detailed understanding of the thermal comfort within the office floors.
Great, yeah, and there was a comment here, and I guess a question for Patricia related to that. Have you looked at IES for building analysis? This person says, I work with an A&E firm. Having access to engineers is key to using the software, so, but it's very powerful, easier to troubleshoot, more than systematic tools. Patricia, any comments on that?
Yeah, I'm a big fan of IESVE. Unfortunately, the price is higher than any other software that we have, and we haven't found that a significant amount of firms use IESVE, but this year for my BPA class, we are going to be implementing IESVE, and I've used it about 4 years ago. It's my preferred software, but it's the one that has the most issues with cost. It's cost prohibitive for certain institutions.
And
even students, there's a prohibition for students.
Right. Well, and maybe this is a good time to advocate for a student version. Also, Patricia, the question about the article you mentioned, can you maybe spell out what journal that's in?
Sure. It's the journal, it's JNIBS, the Journal of the National Institute of Building Science.
Oh,
and
okay, great.
It was in the August edition.
Okay, so this would be August 2015?
August 2015, and that's where the methodology was officially unveiled. So you can find it, most of what I presented in that journal. Now the graphics have changed a little bit because I've streamlined it.
Yeah, great. And so the diagram that you were showing there of the clustering, is that something that is basically a graphic that you've created for a presentation, or is that something that is basically a project organizing software?
No, I created the graphic myself because teaching this over and over again, there needs to be a simple way of explaining it. And I found it's not just with students. I've been asked to present at firms locally, and the graphic helps me to explain the synergies that are most logically clustered together when doing the preliminary BPA.
Yeah, great. And then I think maybe this is for any of you. Have you been looking at strategies that include on-site energy storage, maybe be that thermal or battery electric storage, and or other on-site renewable technologies?
This is Mike. We've done a couple projects recently where we've looked at more campus-level strategies that combine both hot water and chilled water storage, and using heat shift chillers or heat recovery chillers as part of a nighttime strategy to produce hot water and chilled water for storage during the daytime and actually use sort of very robust like forecasting models to look at next day loads and try and pre-make all the hot water and chilled water you need to make so that you can essentially minimize your energy use during peak periods. And I think Stanford is just got done a year ago building a new central plant that is a great example of this, and they've achieved some really remarkable results. And so we've done some studies for other institutions that look at trying to duplicate that and the applicability of it across broader, different climate zones and different types of institutions, and it's really remarkable. It's very replicable.
You know, this is Charles. There's a lot of instances where thermal storage has been used in chilled water or ice, and I think battery storage. The only instance I've seen of this is the RMI Innovation Center. They put a 45 kilowatt hour battery system in, but they did it mostly for their own experimentation. I think before we see much electric storage on site, we're going to have to move towards more dynamic pricing from the utility side. Right now, with even with time of use rates, there's not much of an economic incentive to include storage. But as we get more distributed generation on site, the peak, the utility electric peak is going to shift from late afternoon to early evening, and I think if the utilities move to some sort of dynamic pricing, then it would be then buildings really should incorporate some type of electric storage that would move their peak from 4 in the afternoon when they're and carry them through 7 or 8 o'clock at night when they're and this would be a huge benefit to the utilities, and it won't require a huge amount of storage, but it'll be a benefit for everyone. And I think this is only going to come when we move towards a smart grid and dynamic utility pricing.
Yeah, and the activities in California and the Pacific Northwest in terms of smart buildings and smart grid and are definitely leaning in that direction. And then recently, also, I think ComEd in the Chicago area has gotten a grant to test this methodology. It seems, right now that a lot of the energy storage, especially battery storage, is happening at more of a grid scale than a building scale. But I'm curious for let's say the architects and engineers on the panel, are you beginning to introduce this concept of basically having a grid-friendly building to your clients, and is it something that you're finding any interest in? From NBI's perspective, the potential of buildings meeting these peak demands could be effective and effectively integrated if they're part of the design strategy and operating strategy. What are your thoughts on that? Either, I guess, Michael or Mark.
Sorry, just unmute. This is Mark. The one thing that we've been looking at a lot and really trying to work with clients on is district systems. So whether that be an institutional district or a corporate or more of a kind of civic or neighborhood type of district, there seems to be, even though we talk a lot about net zero buildings, as sort of individual islands, we feel like there's a lot more potential if we think at a bit larger scale, and especially when we start talking about things like energy storage. So with smaller scale buildings, there is definitely, it's harder to incorporate that, or the costs are incremental costs are higher, but if it can be shared at a district level, then we see more potential.
Yeah, and potentially the aggregation by utilities or by doing eco-district activities, have that potential. And also, you know, a conversation I've been having recently is thinking about technologies like combined heat and power for districts that can actually provide that kind of demand response and you know, transactive energy with a utility grid that can be pretty effective as well. So I guess I would ask if there are any last comments from the panel. We are, I think, at the end of our session here, but if you have anything else you want to share. Okay, well, what a tremendous panel. I thank you all for such great presentations, and I would like to let everyone know that this webinar will be available online for you to listen to. It's been recorded, and so you can listen to it again. And we also would like to just remind you, please do complete the survey and provide as much detail as you can, and you'll be able to enter your number for learning units. And we look forward to seeing all of you at our next webinar session. Thank you very much.
Thank you, Ralph and NBI.